So welcome to this lecture. So in the previous lecture we had introduced the notion of path connectedness, and we defined an equivalence relation on X, and we ended the lecture by stating this proposition. So let's quickly see a proof of this proposition. It's really easy. So first we want to show that every path connected space of X is contained in some Xi, right? So let T be a path connected subspace of X, right? And so let X be in T, then X belongs to Xi for some I, right? Now we claim that T is contained in Xi, right? To show that T is contained in Xi, it suffices to show that. So for any, it suffices to show for any T in T, there is a path in X joining X and T, right? But as T is path connected, this implies that there is a continuous path T such that gamma of 0 is equal to X and gamma of 1 is equal to T. But then we can just take the inclusion inside X, which is continuous, and therefore the composite of these is going to be continuous. So this implies that T and X are in the same path component. So this implies that T is contained in Xi. So this proves 1. So we have shown that every path connected subspace of X is contained in some Xi. And to prove 2, this is also obvious, right? So let X be in Xi. So we need to show that any 2 points in Xi can be joined by a path. So this is clear from, okay, so since if X and Y are any 2 points in Xi, then by the definition of, so this is clear from the definition of path components. So both these together prove that each Xi is a maximal path connected subspace of X. Okay, so recall that we had a similar proposition when we were talking about connected components, but that proposition had a third point which said that every connected component is closed. That's not true of the path components. So let's see a counterexample. Right. So a space which is connected but not path connected. Okay, so first consider this. So let's make a picture of this space. So this is 1, and let us take half, and this is 1 by 3, this is 1 by 4, and this is 1 by n, right. So at each of these 1 by n's, we make a straight line of, let us say, length 1. Okay. So and we remove the origin, right. So let us just look at what the space C is. C is a subset of R2, right, and it consists of points 1 by n comma y. So in the x coordinate we have 1 by n, and y, where n is a natural number and y is in the interval 0, 1. Okay. So this will contain all these lines. Okay. So then we also need to take this region. So this is we delete the origin, but we take the rest. So let me just write what this is. This is the points 0, x coordinate is 0, and y coordinate is can be any y, where y is in the half open interval 0, 1. Okay, so in particular this point P is 0, 1. Okay, and then we have to take the so this is this line. Okay, and we also have to take the x-axis, so that's or part of the x-axis, which is union x comma 0. So the y coordinate is 0 over here, and where x, we have to remove the origin, and we can take any x. Okay, so this region in black, so let us say I just make all of them of the same height, 1. So this is our C. Okay, so this is our, so let C have the subspace topology from R2, right. So R2 has the metric, the standard topology, which is the same as the one given by the standard Euclidean metric. Now let gamma from 0, 1 to C be a path such that gamma of 0 is equal to this point 0, 1, which is this point P. Okay. So then the claim is the image of gamma is completely contained inside Y. So what is Y? Y is this subspace, that is Y is this line. Y is this line over here. Okay. So the starting point of gamma is this point P, and the claim is if we take any continuous map from 0, 1 to C, which starts at this point P, then it cannot go outside the subspace Y. Okay. So let us prove the claim. So let us assume, this is not true, right, and that the image, that is the image of gamma moves out of Y. Okay. So note that Y is a closed subspace of C, right? In fact, so C is contained in R2 and it has a subspace topology. From R2 we have the projection to Y, projection to, okay, so this is the second projection to the second coordinate. Right, and the subspace Y is exactly equal to, so let's say this is I. So I compose P2. So P2 is continuous, the projection maps are continuous, and the inclusion is continuous because C has subspace topology, and therefore the composite is continuous, and Y is exactly the inverse image of 0 in C, right? So therefore Y is a closed subspace of C, right? So now we define this set S to be equal to is those x in 0 comma 1 such that the image of 0 comma x is completely contained inside Y. Okay, so let T naught be the supremum over, so S is a subspace of, before we write that, S is contained in 0 1, right, and clearly S is non-empty as 0 belongs to S, right, because gamma of 0 comma this interval which is just gamma of 0 which is equal to P, this belongs to Y. Okay, so then let T naught be the supremum over all S in S. Okay, so we claim that, we first claim that gamma of T naught is in Y. So why is that? So since T naught is the supremum, so this implies there is a sequence T ends in S such that T ends converge to T naught, right. Now this, as gamma is continuous, this implies gamma of Tn converges to gamma of T naught. But note that as Tn belongs to S, gamma of 0 Tn is contained in Y, which in particular implies that gamma of Tn belongs to Y, right, and since Y is closed, every time we have a sequence of points inside Y which converge to some point, so it will mean that limit point is contained in Y. So this implies that gamma of T naught is in Y. Okay, so if T naught is equal to 1, then what does this mean? Then this implies that gamma of 0 comma 1 is contained in Y, which is what we wanted to prove. Right. So then we are done. So let's assume that this is not the case, right? So let us assume that T naught is strictly less than 1. So we have this interval 0 1 and T naught is somewhere over here. Okay, and let's just copy this diagram. And this is our gamma, right. So, gamma T naught is contained in Y, right. So, this point is gamma T naught, right. We just showed that gamma T naught is contained in Y. So, this is our Y. So, we take a small neighborhood U around gamma T naught such that U does not contain the origin. So, we take so U is, let us say, a small neighborhood in R2. Right. So, we could, for instance, take a small square like this, a small rectangle like this. Right. So, this could be our U. Okay. Right. So, then gamma inverse. So, gamma is a map from. So, gamma is a map from 0 1 to C, right, which is contained in R2. So, let us just view gamma as a map from gamma as a map from 0 1 to R2 is therefore continuous because C has a subspace topology, right, and therefore the inclusion is continuous. So, we can just take so then gamma inverse of U, let's viewing gamma as a map from 0 1 to R2 is an open subset, open in 0 1, right, and so it contains the interval T naught comma T naught plus epsilon for some epsilon positive, right. So, now note that as T naught is the supremum of elements in S, the image gamma of 0 comma T naught, this half open interval, is contained in Y. Moreover, we have proved that gamma of T naught is also in Y. So, this implies that image of this closed interval is contained in Y, right. But now, if we take any delta, so if delta is strictly greater than T naught, then gamma of 0 comma delta cannot be contained in Y, yeah, otherwise or else T naught will not be the supremum of S, right. So, thus there exists delta in this half open interval, in this open interval, such that gamma of delta does not belong to Y. So, now we restrict gamma to this T naught comma delta, right. So, this restriction is mapping to C, but the image actually lands inside U intersection C, which is contained inside, yeah. So, therefore, we get that T naught comma delta to U intersection C is continuous, yeah. So, now let us make a picture of U intersection C. So, U intersection C, it looks something like this. So, this is U. This is gamma of T naught, and there are all these lines at 1 upon n's which are converging at x equal to 1 upon n, which are converging to x equal to 0. Okay. And gamma of delta is somewhere over here, right? So gamma of delta is not in y, so it lands outside, and it also lands inside u, so therefore it is of the type 1 upon n comma y for some n positive, right? Right, but now we can find two open subsets, non-empty open subsets in U intersection V. So let's say this is V1, and let's say this is V2, this is V1, right? So then, so U intersection C, we can write it as V1 intersected C, disjoint union V2 intersected C. Okay, so now gamma from T naught comma delta. So this contains gamma of T naught, and this contains gamma of delta. Right. So gamma is from to U intersection C is continuous. So this implies that T naught comma delta can be written as the disjoint union of gamma inverse V1 intersected C gamma inverse of V2 intersected C. Right. But this is a contradiction. As T naught comma delta is connected. Yeah. So this would contain T naught and this would contain delta, right? So that's not possible. So thus T naught has to be equal to 1, and this implies gamma of this entire interval is contained in Y, right? So what does this mean? So this means that if we take a path which starts at this point y, then it has to, at this point p, then it has to remain inside y. It cannot move outside y, right? So therefore, so if this point is, if I take this point, this is 1 comma 1, right? So this shows that, so this shows that there is no continuous path from 0, 1 to C which joins these points 0, 1 and 1 comma 1. Okay. Okay, and so right, so this implies that C is not path connected. Okay. So on the other hand, so it is clear that C minus Y is path connected. Yeah. Why is that? Because if we take any point in C minus Y, so we have deleted this, we have deleted Y. So any point, any 2 points will look like, okay, so maybe I can, so 2 points will look over here. So we can first come from here to the x-axis over here, this point, and then we can travel to this point, and then we can go up. Right. So we cannot do this if our point is on y, because the origin has been left out. Yeah, so we cannot pass through the origin. So it's clear that C minus y is path connected. So this implies that C minus y is connected, right? And so this implies that the closure of C minus y in C is also connected, right? Because if we take any subspace A, then its closure is also connected. Yeah, but the closure of C minus y in C is all of C, because if we take any point on y, yeah, we can find a sequence with the same y coordinate, and this sequence we can find it which converges to y, which converges to this point Q. Okay, so right, so this shows that C has two path components, namely y and C minus y, and just one connected component. Just one connected component C, right? And this also shows that since C minus y is not closed, in C, this implies path components need not be closed. Okay, so we will end here. Thank you.